Hello, and welcome to this video in the metallurgy playlist on phase diagrams as related to welding. To begin with, let me share the screen so you can follow along with the PowerPoint. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. In this video, we're going to look at phase diagrams. Keep in mind that the videos that I am presenting in the Weld Nugget YouTube channel are designed for engineering personnel who might be working with welding, soldering, or brazing, but do not have any technical expertise or educational background in those subjects. Phase diagrams are a graphical representation of phases present in alloys at temperatures ranging from room temperature to melting point. So phase diagrams are diagrams that are drawn, and they represent different phases that will be stable at different temperatures. And we'll see, of course, examples of those in this PowerPoint. Phase diagrams represent phases present at equilibrium. That means these phase diagrams are made where the phases are allowed sufficient time to stabilize at a given temperature. Most phase diagrams, including the ones I'm going to show you today, are binary phase diagrams. Of course, in real life, alloys usually have more than two elements. So obviously, you need more investigation than just looking at that particular phase diagram to understand what exactly is going on in the weld. There are three different types of phase diagrams. There is solid solution, there is eutectic, which is used for solder and braze alloys, and intermetallic, which is common with dissimilar metals and alloys. Before you look at this video, please do watch the previous video that I have posted, Introduction to Physical Metallurgy, where I introduce concepts like metal, alloys, phases, and grains. And that will be useful to watch before going through this one. The simplest type of phase diagram is a solid solution phase diagram. Here I'm showing you a phase diagram where you have copper on the bottom over here, nickel on the right axis, and on the horizontal axis, you see mixture of nickel, increasing amount of nickel. It's 0% nickel, 100% copper at this corner, and with increasing amount of nickel goes up to 100% nickel. On the vertical axis, you can see temperature. It is in degrees centigrade on the left, degrees Fahrenheit on the right. And it starts at 1,000 because from 1,000 to 0 to room temperature, nothing much happens in either of on those scales over here. So we are only looking at this phase diagram from 1,000 degrees up. If you follow pure copper, that would be represented by this vertical axis. So we start, let's say you take a chunk of pure copper, heat it up. It will be solid all the way up to 1085, which is the melting point of copper. And then it'll become liquid. So it goes from solid to liquid at a fixed temperature. The same is true with nickel. If you start with a cube of nickel and heat it up, it will be solid all the way up to 1455 degrees centigrade and then change into liquid at that temperature. Now, let's see what happens when you mix copper and nickel. So let's say you have a 50-50 mixture of copper and nickel, which will be right in around the middle, and you keep heating it up, and you find yourself in this region over here. And the interesting part about this solid solution is essentially that implies that copper and nickel are completely soluble in each other. That means they mix with each other in any ratio. So you can mix 1% of copper in nickel or 1% of nickel in 99% copper, and they will completely mix like sugar dissolving in water, and they won't form any reaction products, and they won't form any phases other than just the mixture. So the solid phase of copper and nickel is uniform all the way in this phase diagram. The only time something changes, if you take that 50-50 mixture, keep heating it up, and once it reaches this temperature, the lower line, that is when it starts to melt. The only difference between a mixture of copper nickel melting compared to copper or nickel is that the copper nickel mixture melts over a certain temperature range. It doesn't melt instantaneously at one temperature. So when you heat up the mixture, it will go up to this line, some of it will start melting, and as you increase the temperature, more and more of it will melt till you reach the upper line, which is called the liquidus line, where all of it melts. And then if you increase the temperature just keeps increasing, and we have a liquid mixture of copper and nickel. So this is a very simple phase diagram, typically called solid solution because they dissolve in each other. There are no reaction products. That's the main thing. And the diagram looks very simple. Examples are, of course, copper and nickel, titanium and zirconium, silver and gold, platinum and palladium. Platinum palladium is a common mixture or alloy which is used in medical devices. So that phase diagram is very similar to this as well, just the temperatures are different. Now, just because copper and nickel mix homogeneously and comfortably into each other does not mean that their properties are linear. So, for example, in this case, copper is conductive, nickel is fairly conductive, but the copper-nickel mixture is actually very hard, resistive, and a very poor thermal conductor, which is a very surprising aspect. So on this chart, I'm showing you thermal conductivity of a mixture of copper and nickel. And on the left axis, we have pure copper. As we increase the amount of nickel, you will see that the conductivity, thermal conductivity in this case, drops very quickly, even with 5% nickel in copper. So the properties of copper nickel are not linear. So even though the diagram looks pretty simple and straightforward, the material properties of the mixture are not linear. So even a small fraction of nickel can significantly affect the behavior of the mixture. So in fact, copper and nickel, the alloys or mixtures of copper and nickel are actually used as resistive elements, so which is very interesting. So looking at the phase diagram, so that is something to keep in mind. Looking at the phase diagram, you cannot predict the behavior of these phases. So only thing you can know is what type of phases are going to form. To study the behavior, you still have to conduct measurements and tests. The other type of phase diagram is a eutectic phase diagram, which is commonly encountered in solders. So in this particular phase diagram, I'm showing you lead on the vertical, on the left corner, tin on the right corner, and the temperature is on the vertical axis here. You will notice that this diagram looks a little bit different. So this diagram has a melting point. We have a lead melting point of 327. So if you take solid lead and keep heating it up, it will melt at 327. If you take pure tin and keep heating it up, it will melt at 232. Now in the previous diagram, which I showed, all the other melting points were between the melting point of copper and nickel. So all the melting points of mixtures were higher than the melting point of copper over here. Now, however, we have a situation where a mixture of tin and lead, 61.9% tin, and the rest is lead, the temperature melting point of that mixture is actually lower than the melting points of either lead or tin. And that melting point is at 183 degrees centigrade. And that is how these diagrams got the name called eutectic phase diagrams. Eutectic is a Greek origin, means melts easily. In this case, obviously, we see that melts at a lower temperature. And that is the uniqueness of eutectic phase diagrams. There is a melting point, a mixture whose melting point is going to be lower than the mixture, than the original phases. Couple of interesting things about this phase diagram. You see over here, there is a region where lead can dissolve some amount of tin. So it's a single phase. Over here, we have a narrow region where tin can dissolve a very, very tiny amount of lead, and that solubility goes to zero. So at room temperature or close to room temperature, there is very little solubility of lead and tin into each other. So this diagram is exactly opposite. Lead and tin do not want to react, but they also don't want to mix. So when you cool a mixture of lead and tin, and you look at the mixture, you will find a very fine distribution of regions where there are pockets of lead, and next to it, there's a pocket of tin. So this kind of distribution where they don't want to react, but they don't want to mix, but they want to separate is very unique of eutectic behavior. You will see this region over here called pasty region. So this is how you deal with solders in terms of how they behave when they melt. If you take a eutectic solder and you heat it up, once it goes to that temperature 183, it will immediately melt. So it almost behaves like a single element. Just as lead and tin have a single melting point, eutectic mixtures have a single melting point. However, if you are slightly off eutectic, let's say you have a 50-50 mixture, and keep in mind this scale over here is not linear, so that's why the spacings look a little bit odd. But ignore that. If you take a 50-50 mixture and you heat it up, it will come to this point over here where some amount of that mixture will start melting at 183. And then you have to continue to heat it up to a higher temperature before the entire mixture becomes liquid. So here again, there is a melting range similar to what we had in copper nickel in the mixture. There's a melting range. Now, how do we take benefit of that melting range? In that melting range, where you are in the middle over here, where it's partially solid, partially liquid, the solder alloy is quite viscous. And we can use that behavior to bridge larger gaps between components. So you can tailor the molten behavior, not completely molten, but partially molten behavior to your benefit in process control if you're trying to bridge smaller or bigger gaps. If you're trying to bridge very thin gaps, then a eutectic mixture is good. But if the gaps between components are bigger, then a non-eutectic mixture would be beneficial to bridge those gaps. Here's an example of a cross-section of a solder connection. And you will see in this solder, this is a solder alloy over here, and you can see dark and light gray regions of lead and tin, which have separated out. And they are not reacting, but they don't want to mix either. So it's very unusual. So this is exactly opposite of a copper-nickel mixture. Of course, now you might have heard of lead-free solders because lead is considered a harmful element. So lead-free solders are gaining popularity. In lead-free solders, there are mixtures of tin, copper, and silver. So that's a different mixture than lead-tin. Another common eutectic, which is popular in this case for brazing, is a silver-copper eutectic. Here again, you have 100% silver in this corner, 100% copper over here, and the temperature in this case starts from 200 because nothing interesting happens down to room temperature. Here again, you will notice that the melting point of silver is 961, melting point of copper is 1085. However, the melting point of 28.1% copper and the remaining silver, that mixture has a melting point of much lower at 779 degrees centigrade. So the silver-copper mixture also is a popular, in this case, a braze alloy because the temperature is much higher than the tin-lead mixture. So this is a common braze alloy. It forms a family, actually. They take silver copper and then they add a whole bunch of things as required to fine-tune this melting range. So you might have silver copper with cadmium, with zinc, with a whole bunch of other things for different applications. So you could go to a website and have 10 different silver copper based braze alloys. So if you're in the business of brazing, then you have to very carefully select, or soldering, brazing or soldering, you have to very carefully select the chemistry of the solder alloy. It is not just enough to say, okay, let's get a tin lead solder. You need to understand what is the ratio of tin and lead, or what is the ratio of silver and copper that you need to use for that particular application. Another type of phase diagram is an intermetallic phase diagram. That is a phase diagram where you see a lot of vertical lines and different regions over here. This is very common in situations where there is a lot of reaction between the two elements. In this case, I'm showing you a aluminum copper phase diagram. So we have aluminum on the left corner here, copper on the right corner, and in the middle is a mixture of aluminum and copper. When you see a lot of these vertical lines over here, that tells me that there are a lot of reactions between aluminum and copper and form different reaction products. Almost always these reaction products are brittle. So just looking at this phase diagram, I would predict that if you weld aluminum to copper with a lot of mixing of the two, you are very likely to have, under normal circumstances, you are very likely to have cracks in the welds. So there are different ways that you can use phase diagrams. You can use phase diagrams to understand what are potential, of course, phases that form. And then you can look at different melting points of these different phases, reaction products, what to estimate. And these all end up being a good starting point for your analysis of what you're trying to do. So phase diagrams, in summary, phase diagrams provide a starting point for the analysis for solder, braze, and welds. So the first thing you want to do is, if somebody says, okay, let's weld titanium to nickel or something like that, the first thing you want to do is go on the internet and look for a titanium nickel phase diagram and see which type of phase diagram it is. Is it a solid solution? Is it a eutectic? Or is it intermetallic? That provides you a good starting point for the analysis. Keep in mind, so these provide a good insight on what to expect. Again, ultimately, what you need to do is you still need to make the welds and conduct analysis to confirm what you're seeing from the phase diagram, since it's not always predictable. One of the reasons it's not predictable is because you can have multiple alloying components in these alloys. So say somebody says, let's weld titanium to nickel. The titanium itself may not be pure titanium. It might be a titanium alloy, or the nickel itself may not be pure. You might be welding a nickel alloy. So the result of the mixture of a titanium alloy welded to a nickel alloy may not exactly match what you are going to see from a clean titanium welded to a clean nickel. So you do need to do some additional analysis in terms of making welds, measuring the hardness, conducting some mechanical testing of the welds to fully understand what is going to happen. One thing to keep in mind is these phase diagrams are equilibrium phase diagrams. That is, these phase diagrams are based on slow cooling. So they assume that when you make a mixture and you heat it up and you cool down, you're cooling down very, very slowly. And unfortunately, most of the welding we do, we don't have the luxury of cooling it down slowly. In fact, many times we are cooling it down at an extremely, extremely fast pace. Sometimes on the order of 1,000 degrees a second or even 1,000,000 degrees per second. So it does happen that there are situations where the phases might be sluggish, or they might transform into a phase which is not familiar or not occurring on the phase diagram. An example is the iron-carbon phase diagram, which all the steels are based on, and they contain a phase, not the phase diagram, but they can produce a phase called martensite, which occurs only due to rapid cooling. So keep in mind that phase diagrams are a great place to start your analysis if you're trying to understand a particular weld. But keep in mind, there are a lot of exceptions because of the alloying, because of the cooling rate, where what you get in the weld might be a bit different or sometimes a lot different than what you get on the phase diagram. So this is a great starting point, but do not stop over there. Conduct metallurgical analysis, conduct mechanical testing before you draw any conclusions. Well, thank you for your time. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel, The Weld Nugget, by clicking on the subscribe button below. And there are many other videos on specific topics in different playlists on this channel. So feel free to browse through them and see if you find something interesting. I want to wish you the very best and hope you enjoy your experience in welding.